In this Easy Ed video lecture, we are going to start with the introduction of complex numbers followed by equality of complex numbers. Next, we move on to the conjugate of complex number, geometrical representation of a complex number, algebra of complex numbers, and different forms of a complex number. Then we learn how to find the modulus and argument of a complex number, and finally, square root of a complex number. Let's first consider what we know about quadratic equations, so we can better understand where complex numbers are coming from. Suppose we want to solve the quadratic equation x squared minus 4x plus 20 equal to 0. We know that x is equal to minus b plus minus square root of b squared minus 4 times a times c over 2 times a. On solving, we get 4 plus minus square root of minus 64 over 2. This gives us a problem. Under the square root sign, we have square root of minus 64. Can we find such a root? To allow such roots around the year 1800, the concept of square root of minus 1 was proposed and is now accepted as an extension of the real number system. The symbol used is I equal to square root of minus 1. Here I is called the imaginary number or imaginary unit.
Seriously, pay attention. This is important.
Remember, I equal to square root of minus 1 implies that I square equals to minus 1. Let us now define complex numbers. A complex number is a number of the form x plus iy, where x, y are real numbers and I equals square root of minus 1. It is denoted by z. So we can write z equals x plus iy. Here x is known as a real part of z, denoted by rez, and y as the imaginary part of z, denoted by imz. Note that you can write a complex number as x plus iy or x plus yi. There is no difference in their meaning. We now return to our problem from above. We didn't know that what to do with square root of minus 64. Now we can write the solution using complex numbers as follows. 4 plus minus square root of minus 64 over 2 is equal to 4 plus minus I times square root of 64 over 2, which on solving gives 2 minus 4i and 2 plus 4i as the solutions. Next, let us understand the meaning of two complex numbers being equal. If z1 equals a1 plus ib1 and z2 equals a2 plus ib2, then z1 equals z2 if a1 equals a2 and b1 equals b2.
Seriously, pay attention. This is important.
As two complex numbers are not comparable, order or inequality is not defined for complex numbers. Let us now see how we can use the idea of equality of complex numbers to solve for x and y. Suppose we want to find x and y for this question. For solving, we compare the real and imaginary parts. Comparing, we get 3 over root 5 times x minus 5 equals root 2, and 2 times root 5y equals 0. On solving further, we get x is equal to root 5 by 3 times root 2 plus 5 and y is equal to 0. Let us now understand the meaning of conjugate of complex numbers. For z equal to a plus ib, conjugate of z is z bar equal to a minus ib, which is nothing but the reflection of point z about x-axis. Let us now see how a complex number is represented graphically. A complex number, a plus ib, can be represented as an ordered pair a, b, and thus as a point in a plane known as complex plane or Argand diagram. Here, the x-axis is called as real axis, while the y-axis is imaginary axis.
Hey, it's time to concentrate now.
In this representation, multiplication by I corresponds to a 90-degree rotation in the counterclockwise direction, and the equation I square is equal to minus 1 is interpreted as saying that if we apply two 90-degree rotations about the origin, The net result is a single 180-degree rotation or a flip from 1 to -1. And if we think about it more, we could rotate twice in the other direction clockwise to turn 1 into -1. This is negative rotation or a multiplication by -I. Now what happens if we keep multiplying by I? The answer is in the graph. 1 times I, 190 degrees rotation counterclockwise giving I square, 2 rotations counterclockwise giving -1. I cube, 3 rotations counterclockwise giving -I. I power 4, 4 rotations bring us full circle to 1. I power 5 again takes us to I, starting the whole cycle again. Next, we move on to the algebra of complex numbers. We start with the addition of complex numbers. If Z1 equals A1 plus IB1, Z2 equals A2 plus IB2, then Z1 plus Z2 equals A1 plus A2 plus I times B1 plus B2. It basically says add real parts, add imaginary parts. Next, we look at subtraction of complex numbers. If Z1 equals A1 plus IB1, Z2 equals A2 plus IB2, then Z1 minus Z2 equals A1 minus A2 plus I times B1 minus B2. It basically says subtract real parts and subtract imaginary parts. The next operation is the operation of multiplication. If Z1 equals A1 plus IB1, Z2 equals A2 plus IB2, then Z1 times Z2 equals A1 A2 minus B1 B2 plus I A1 B2 plus A2 B1. Finally, we have the division operation. If Z1 equals A1 plus IB1, Z2 equals A2 plus IB2, and Z2 is not equal to 0, then Z1 over Z2 equals A1 plus IB1 over A2 plus IB2. Multiplying the numerator and the denominator by A2 minus IB2, the conjugate of the denominator, and simplifying, we get A1 A2 plus B1 B2 plus I A2 B1 minus A1 B2 upon A2 square plus B2 square. Let us now look at the different forms of a complex number. The first one is the Cartesian or rectangular form. If x and y are real numbers, then z is equal to x plus iy is called the Cartesian form of the complex number. Next is the polar form. Next, our aim is to write complex numbers in terms of a distance from the origin and a direction from the positive horizontal axis. We find the real and imaginary components in terms of r, the length of the vector, and theta, the angle made with the real axis. From Pythagoras' theorem, we have r square equal to x square plus y square, and basic trigonometry gives us tan theta equal to y by x. Therefore, x is equal to r cos theta and y is equal to r sin theta. Multiplying the last expression throughout by I gives us iy equals ir sin theta. So we can write the polar form of a complex number as z equal to x plus iy equals r times cos theta plus I sin theta. Finally, we have the exponential form. We just saw that polar form of z is z equal to r times cos theta plus I sin theta. Also, by Euler's equation, we have cos theta plus I sin theta equal to e power I theta. Hence, exponential form of z is z equal to r times e to the power I theta. Let's multiply two complex numbers in polar form. Let z1 equal to r1 cos theta 1 plus I sin theta 1 and z2 equal to r2 cos theta 2 plus I sin theta 2 be two complex numbers in polar form. This implies z1 times z2 on multiplication, and simplification gives us r1 times r2 times cos of theta 1 plus theta 2 plus I sin of theta 1 plus theta 2. This says to multiply two complex numbers in polar form. Multiply the moduli and add the arguments. Let's now divide two complex numbers in polar form. Let z1 equal to r1 cos theta 1 plus I sin theta 1 and z2 equal to r2 cos theta 2 plus I sin theta 2 be two complex numbers in polar form. If z2 is not equal to 0, then z1 divided by z2 on division and simplification gives us r1 by r2 times cos of theta 1 minus theta 2 plus I sin of theta 1 minus theta 2. This says to divide two complex numbers in polar form. Divide the moduli and subtract the arguments.
Seriously, pay attention. This is important.
Next, we define the modulus or absolute value of a complex number. Let z equal to x plus iy or r times cos theta plus I sin theta. Here r is called the modulus or absolute value of z and is denoted as shown. Hence, absolute value of z equals square root of x square plus y square, which is further equal to r. But how did we get this expression? This is how we got it. Absolute value of z is the same as absolute value of x plus iy, which is again same as the absolute value of r times cos theta plus I sin theta. On simplification and using the property that cos square theta plus sin square theta equals 1, we get the required expression. Also in the figure, theta is called the argument of z and is denoted by argument of z or amp of z. Hence, argument of z equals theta, which is further equal to tan inverse of b by a. Argument belonging to the interval minus pi to pi is called principal value of argument. Next, we move on to the steps for finding the principal value of arguments are. Step 1. Find theta is equal to tan inverse of absolute value of b by a for theta belonging to the interval 0 to pi by 2. Step 2. Identify in which quadrant a, b lies. Step 3. Use the following diagram to find out the principal value of argument based on the value of theta and quadrant from step 1 and step 2. Let us find the principal value of argument in minus 2 times square root of 3 times I. First, find theta by calculating tan inverse of absolute value of minus 2 times square root 3 over minus 2. This is equal to pi by 3. Next, check the quadrant. Minus 2 times square root of 3i lies in the third quadrant. Finally, we use this graph to calculate the principal value of argument in minus 2 square root 3i. Since minus 2 square root 3i lies in the third quadrant and the value of theta is pi by 3, therefore the principal value of argument in minus 2 square root 3i is theta minus pi, which is equal to pi by 3 minus pi, which is further equal to minus 2 pi by 3. Further, let us understand how to calculate the square root of a complex number, that is to find square root of a plus ib. Let x plus iy equal to square root of a plus ib. Squaring both sides, we get x square minus y square plus 2 times ixy equals a plus ib. Comparing the real and imaginary parts, we get x square minus y square equals a and 2xy equals b. This implies x square plus y square equals square root of x square minus y square whole square plus 4x square times y square. But how? Then find x square, take positive value of x. Find y square, take value of y which satisfies 2xy equals b. Note if b is greater than 0, x, y are of same sign. Else if b is less than 0, x, y are of the opposite sign. Square root will be x plus iy. Other root will be x minus iy. Let us now try to find the square root of 8 minus 15i. First, let x plus iy equal square root of 8 minus 15i. Squaring both sides, we get x square minus y square plus 2 times ixy equals 8 minus 15i. Comparing the real and imaginary parts, we get x square minus y square equals 8 and 2xy equals minus 15. Note x and y are of opposite signs. we get x squared plus y squared equals 17. This is, on solving further, gives x equal to plus minus 5 by root 2. Now for x equal to 5 by root 2, we get y equal to plus minus 3 by root 2. As x times y is equal to minus 15 by 2, therefore for x equal to 5 by root 2, y equal to minus 3 by root 2. Therefore one of the square root is equal to 5 by root 2 minus I times 3 by root 2. And the other square root is equal to 5 by root 2 plus I times 3 by root 2. Let's have a quick review of what we have studied in this lecture. We started with an introduction to complex numbers. Then we learned about equality of two complex numbers. Next, we understood the meaning of a conjugate of a complex number. Then we saw the geometrical representation of a complex number in the form of an Argand diagram. Then came the algebra of complex numbers that included addition, subtraction, multiplication, and division of complex numbers. Then we saw the different forms of a complex number: rectangular, polar, and exponential. Next, we defined the modulus, an argument of a complex number. Then, we saw the steps for finding the square root of a complex number.